Testing, testing. Testing, 1, 2, 3. Testing, 1, 2, 3. Okay, so I will continue with our lecture. So the other day we left one examples for the case of Poisson distributions. So today we're going to finish these examples and then we proceed with normal distributions. So in example 3, it was told that the numbers of industry injury per working weeks in a particular factories is known to follow Poisson distribution. So from here we happen to see that this is a case of Poisson. And what is the thing that we discuss distribution here is that we are discussing the number of industry injury. And if you happen to see that they're talking about per week and then to the number of injury per week. With all this idea here, now we will begin our solution. We identify what is our x referring to before we start our solutions. So in here, refer my x. I will let the x is happen to be number of industrial injury. And once again, I doesn't include the time period there is because later in this happen to be changing. So the time period I will happen to mention in the distributions later. So let's see part A. We happen to know that we want to find the probability that in a week. So in here we refer to a week. So the time period is same as what is mentioned in the information for. So therefore, this one for part A, we will continue with X follow Poisson distributions with the mean of 0.5, which this is spent for the case of in a particular week. We just write in a week lah. Then now, what we want to find from the case here, where first we want to find the probability such that there will be less than 2 accidents. So in here, the number of accidents is referring to the number of industry injury. They are referring to the same thing. They are referring to the same thing. So therefore, in this case here, our answer for part 1 will happens to be Px less than 2. And in order to find this answer here, guys and girls, we are going to make use of statistical table. Instead of doing formula calculation, we use statistical table. If less than case, we can convert it in the form of greater equal, where we want to use greater equal because this is how we interpret from the table. So therefore from here, I'm going to use 1 minus so that I'm able to switch the sign here from less than become greater. So the idea of 1 minus will happen to be the P is still P itself, the X is still X itself, 2, the value of 2 is still 2. The changes will happen on the sign. Less than will turn out to become greater. So originally without equal sign, so in 1 minus, we add in the equal sign. And next, we refer to statistical table such that our lambda is 0.5. And also for the R equals to 2, you should able to find out that you have the answer 1 minus 0.0902. And as a result, the answer is 0.9098. So this is the probability that less than 2 accidents happens. Okay, proceed. The next part of the question is talking about, let's see, we want to have the case of more than 2 accidents happens. So more than 2 accidents happens, which is means that we are referring to part 2. We have our x is greater than 2 because more than 2, so x greater than 2. And if I want to convert this one into some form that I can make use of statistical table. So what I can do here is that I'm going to consider in such that, so I have the sign greater. So I don't do 1 minus here, but try to think in logical sense that from greater, if I want to change to greater equal, for the case of discrete, then it should greater equals to what? So think about it. If you want more than 2, that means if in the discrete case, more than 2, that means I want from 3 and onwards. And from 3 and onwards, therefore I know is greater equals to 3. So this is equivalent to x greater equals to 3 in the case of discrete. And once again, you can make use of your statistical table such that you find lambda equals to 0.5 and your r equals to 3, and you should get direct answer from the table, and it gives us the answer just 0.0144. And this is how we get the answer for the part A, where the lambda is equivalent to the mean value given. So the reason why it is equivalent is because the time period discussed here in part A is the same as the information given, which is discussed on 1 week. Next, when the time we go for part B, what happened in part B is that we are considering there will be no accidents. So there will be no accidents. So by right, based on our interpretation, there is no accident. I know that it should be referred to x equal to 0. However, guys and girls, be careful here because in Poisson distribution, you must be always alert about the time periods or the space involved in the question. All the while we're doing just now in part A is that we discussed in 1 week. But now what happened is in part B, the questions, the time period is changed to 3 weeks. So therefore, your distribution X, we need to make some adjustment where the lambda here is no longer 0.5, but we just consider as this way, 1 week, if it happens to be 0.5, 3 weeks, then we will have 0.5 times 3. So we have 1.5. As a result now, your lambda we consider as 1.5. And when the time you go for your calculation, again, remember, we are going for lambda equals to 1.5. And once we are clear about this thing here, let me add in more info in my distribution where I want to describe this is in 3 weeks periods. So in a 3-week period, if there is no accidents occur, so what will be my result and how can I calculate it? So it will be px equal to 0. So at this moment here, again, it's up to your choice whether you want to use formula or you want to use table to do this calculation. So the reason is because just one value x equal to 0. So it's up to your choice whether which one you want to use. And let's say in this case here, I still want to use table. So I will have 1 equals to. So again, if I want to use table, I'm going to make use of the idea of, sorry, I have p x greater equals to something minus px greater equal. The first part that I highlighted in blue, the greater equal, should include the value we want. The one behind is the one that we're going to subtract. We're going to take out whichever x value that we don't want. So in this case here, you notice that we want x equal to 0 only. So you should be having x greater equals 0. And once again, use our logical sense to do analysis. Case of discrete, that means I'm referring for the case 1, we are referring to the case start from 0, 1, 2, 3, so on so forth until infinity. However, if you notice, what we actually interested here is that we just want the 0. Start from 1 and the rest we don't want. So therefore, the thing that we want to minus is 1 and onwards, which give us we minus px greater equals to 1. And based on table, px greater than 0, that means you refer to lump down as 1.5, the r as 0, so you find out that the answer is equals to 1, minus, then for the case x greater equals to 1, you refer r equals to 1 for the same lambda value 1.5, then you will somehow find out the answer is 0.7769. And as a result, when the time you simplify further, you got 0.2231. And there goes your answer of part B. Okay. Although the examples here is limited, I hope that you're always alert lah. When the time you do Poisson distribution, you must alert in the sense of the changes happens in the time periods or the space. So in this case here, part B, instead of referring to 1 week, now we are discussing 3 weeks. Or maybe some question they can discuss in days or in months, depends, but you need to alert about the changes on the time periods. Okay, then we will go on with normal distributions. So here, I just would like to go through quickly on some of the criteria, the things that I want you to take notes in normal distributions. What I described here in my screen here is different from what you have in your PowerPoint slide. Where your PowerPoint slide, there is many slides to discuss what is going on there. But basically, I'm just going through in one or two here. Then we will go direct to the example one. Okay. First, normal distribution. The first thing what you need to know is that how we write the normal distribution. So whenever the question asks you to write distribution, that means that you're referring this one. You describe the random variable follow. So n means follow normal distribution. And for normal distribution, the parameter will be mu and also sigma, which is the mean and also the variance. And this info somehow you can get from the question. Go on. When the time we talk about normal distribution, you find out that to solve the normal distribution question, we mainly based on table. I believe this question somehow like you encountered before in your SPM level. We solve normal distribution question referring to table. We doesn't use any normal distribution formulas to solve the probability. Although there is a formula there, but we rarely use. And in order to make use of the table, you need to understand the graph of the normal distribution. First of all, you find out that normal distributions, you have a symmetrical bell-shaped curve. So here, I have a bell-shaped curve. This is called a bell-shaped curve. It is symmetrical where you happen to find out that when the time I happens to draw a line, I cut the graph at this line here, you find out that left-hand side and right-hand side, they happen to mirror image to each other. It happens to be symmetrical. And it's symmetrical about the mean of the distribution, where for information, the mean of the distribution, which is happen to be located at this straight line here. And you can see even clearer in the following diagrams. where the red dotted line here indicates that the mean, the mu, which is the mean. And since it's happened to be symmetrical, what you happen to see is that you was told that the total area under the curve is always equal to 1. Then the area, when the time I cut the graph is such that pass through the mean, the left-hand side and right-hand side, they should have the same region, 0.5 and 0.5. The total region equals to 1. Again, why is this equals to 1? Because for information, normal distribution is actually considering a special case of continuous random variable. And what we know about continuous random variable is that integrations from infinity to infinity for our PDF will always equals to 1. So when the time you integrate this graph here, you find out that the integration is referred to the region, and total regions will happen equals to 1. This is what it roughly means here. Okay. Later, you find out that there are small things that we can describe using the idea of symmetrical. Why we want to mention the word, the graph is symmetrical? Because this is the important criteria that help most of our calculations later. Go on. In normal distribution, you will find out that before we can start our calculation, we do some conversions that we call it as the standardizations. And what the standardization do is that we convert any, for example, x equals to normal distribution mu sigma square, any value of mu, any value of sigma square that is relevant, we can always convert into the standard normal distribution. The table we use is referred to the standard normal distribution. And it's very important that why we want to make use of the standard normal distributions. Later we will see by our applications. And how the standardization go on is that you just need to remember, you take the x minus the mu, divide by the sigma, and this will happens. And you see, basically what happens if in terms of graph is that initially, your mu is still at the center. I put dotted line there is to indicate that it is at the center. But when the time you go for standardization, you will find out that your mu will turn out to become 0. And the dotted line is actually now located at the vertical axis, or usually we call it as a y-axis. Okay. Okay, go on. Why is so important that we want to convert into standard normal, and also that the graph is happen to be symmetrical? So guys and girls, the idea that I need you to be aware is this one. Looks very nice here, but I hope that you can imagine and get the idea there. Okay, so let's say this is happened to be my bell-shaped diagram of the normal distributions. If in the standard case, then the middle line here will happen to be 0. So what it happens to tell us about the symmetrical properties of the bell-shaped diagram is that, let's say I have a value here. Let's say I simply put a value, let's say 0. Then the regions now I highlighted in blue, I shaded in blue. Let's say here I have the value of alpha. Then by right, I will have another regions have the same area, which is alpha on the right hand side, such that it will happen that this region now I highlighted in blue is also alpha, and the corresponding value that I have on the horizontal axis will be the negative of the right hand side one. They have the opposite sign. Again, this is the case that we discussed about standard, which is the mean is 0. Similarly, these regions now I highlighted in yellow, and the one I highlighted in green will also be equal to each other because, again, the symmetrical properties. Once you're done with this, the next thing I want you to see is that we want to refer on the statistical table on the normal distributions. where in the normal distributions, the statistical table according to your statistical book, we have the Z value starting from 0 in 2 decimal places until 4.09. All is start with 2 decimal places, and how we happen to read from the statistical table is that, again, we're going to read based on greater equal. And one thing I want you to take notes also in this case here, since normal is a continuous case, so when the time you doesn't have equal sign on the inequality greater, it still happens to bring the same value for the probability with the equal sign. So these two are happen to be the same in the remark for normal distribution. Go on. How we happens to read the statistical table here? So let's say I put one simple examples here to review, to revise. So first of all, I must make sure I have convert my statistical table into I convert my distribution into the standard normal distribution. It turned out become Z, let's say 0 point, and make sure you convert into 2 decimal places so that we can make use of the table. Let's say 0.3. And how I get the 0.34? So guys and girls, first of all, you refer to 0.3. You refer to 0.3. Then 0.04, how you're going to get it is that you refer to column and you find out that 0.4 is at here. So basically, as if like you take these two values, sum up, it should be the value that you want to find out. And therefore, 0.3, 0.04, it happened to provide us this value, 0, the answer for exact greater equals to 0.34. Okay. This is how we happen to read the. And in the later example number 1, we will try to learn on how to, not only how to read from the table, but what is the value we want to read from the table. And we need the help of the bell-shaped diagram in the later parts. So let's go for example number 1, where you're given the case that we already have all the distribution in the standard form. So let's see. How I know it's happened to be in the standard form is that you see you have Z follow normal distribution 0, 1, where the mean is 0, the standard deviation, the variance is 1. So now, how we happen to make use of our statistical table to calculate all this? Again, in order to make use of statistical table, you must make sure it happens to be Z greater equal, or you can also use Z greater to find the answer from the table. So let's see. Question A, I have PZ greater equal 2.5. So in this case here, by right, I can just directly get my answer from the statistical table. So I want 2.5. Let's see, where can we get the 2.5? Let's go for the table, have a quick look. So let me enlarge it so that you can see where is the 2.5. So 2.5, first of all, we refer to this part here, the side here, refer to 2.5, and we find 2.5 here. We find 2.5 here. And 2.5, if you want to have 2.5 only, that means you need to refer to 2.50 in the table, and 2.50 we're referring to taking this part here, 0.00 plus with your 2.5, and therefore your answer will be this part here. The answer is 0.0062. As simple as that. So therefore, we state our answer. We have it equals to 0.00621. Okay, so this is just a warm-up. The next part, part B. Part B, and make sure you pay attention because this, I have more things to write, more things that you need to take notes. Part B. I have PZ greater than 0.5. So how can I get the answer here? Although we say that table, we can use, we must make use of Z greater. But if you notice, all the value that we refer for the case of Z greater is referred to positive value. However, in these examples here, you find out that this value is negative value. Then how are we going to solve it? And is it possible to solve it? I want you to pay attention on the diagram I'm going to sketch, where I make use of the diagram to interpret the situation and apply the properties of symmetrical to solve the question. So let us represent the situation in here in our bell-shaped diagram. Of course, is 0. So I want first refer to this value here, negative 0.6. So negative 0.6 somewhere on the left of my 0. So let's say here, negative 0.6. And what I want is that I want the case of Z greater than negative 0.6, which is, means that I would like to use Z greater. And whenever you draw the diagrams here, you find happen to be greater than 0.5. That means half of the bell-shaped diagram. That means this is not possible to direct get the answer from the statistical table. We need to make some adjustment. Or maybe if the region on the left also, we cannot do so. So let's say now, how I'm going to solve here is that, so use our logical thinking. If you want to find these shaded regions, what you can do is that you one is the overall regions minus the part that you don't want. And this one minus here, please be aware, dia tak ada kaitan sangat, mungkin tak ada kaitan sangat dengan yang one minus kita buat biasa. Mungkin dia akan nampak ada sikit beza dari sign and so on so forth. Okay, anyway, I just continue with the one minus concept. Since I know I want to use one minus concept, I will have one minus. So in here, if let's say I stick to the rules that I do for one minus, it will happen to be Z is still Z. The value negative 0.6 is still negative 0.6. What happened the next is that the inequality sign will change to less than, and equal sign we need to insert because previously we don't have equal sign. And come up to here, how far it will be helpful to us is that, so guys and girls, if you notice, this part I highlighted in blue is actually refer to these regions here that is empty. And let's say I redraw another diagram. I draw another diagram to represent this part highlighted in blue so that you have clearer visions to see how I get my further answer. So I find out that at the point negative 0.06, let's say at this part here, I have a region of alpha. These regions, I'm not able to get the answer from statistical because the regions is happen to be on the left-hand side of the graph. So I can only get the answer if, let's say, I have on the right-hand side and also alpha. Then it is equivalent to each other. And you notice that memang akan exist because the graph is symmetrical. And based on what we see just now, kalau region dua-dua ini sama, then the value of the horizontal axis here will be just opposite side of what we have on the left. So if left is 0.6, on the right we have just 0.6 opposite side. And based on here, we can somehow see that this part here is actually can consider as Z greater equals to 0.6. Now, Z greater equals to 0.6 is something that we can get from the statistical table, this one, greater than 0.6. So I will just proceed with the answer, not to waste too much time to keep on refer to table, to show you how to refer to table. So I have the answer as 0.2743. So as a result, 0.7257 will be our answer. So this is the result for part B. Before we go on with the further questions, so for normal distribution, what I will suggest you is that as a beginner, kalau you memang tak bagus dalam interpret ini punya, you bolehlah as a beginner, you try to make use of the diagram. Mungkin at the beginning you perlu draw a few bell-shaped diagram to analyze from one to another, like what I'm doing now. As you can see, initially I interpret dapat bell-shaped diagram dalam hijau ini. Then the next part, the part highlighted in blue, I happen to interpret the following bell-shaped diagram in red. I seolah-olah macam leceh untuk draw dua kali untuk tengok apa berlaku. Sebab kalau kita tak nampak jelas, memanglah the lukisan will be help a lot. And from the same diagram, it give me the answer highlighted in yellow. Next, we'll go so that we see how powerful is the diagram to solve such questions. See, we have P minus 2.23 less than Z less than negative 1.23. Okay, so please be aware on how to solve these questions here. Because maybe saya perlu diagram yang banyak untuk describe. So again, kalau sudah standardized dalam Z form, without further ado, we try to sketch a bell-shaped diagram. Anyway, bell-shaped diagram is not a compulsory solution, not a compulsory step, but I will always make use of it to help me to decide answer. Middle is 0, so I want negative 2.23 until negative 1.23 as the region. So let's say this is the regions, this is the part that I have negative 2.23. Here I have negative 1.23. Of course, you must make sure the arrangement of the number is. So saya nak kawasan ini sebagai jawapan. And once again, kawasan ini pada sebelah kanan of your diagram. Able to get the answer directly from here because